Hello to everybody and welcome to the second lecture of MHM 427AT. Before starting our second lecture, let me just give you a bit of overview what I've told you during the last lecture. In the last lecture we talked about radiation. We said that radiation is the only form of heat transfer happens in vacuum. We talked about the index of let me write it down for you. We talked about the index of refraction, we defined it as a CO to C, which is like the speed of light in vacuum and speed of light in medium. We said that okay, that's clearly needs to be bigger or greater than 1 for the most of the materials. We said that for air and gases is more or less equal to 1, for glass is equal to 1.5, and for water is 1.33. Beside that, we talked about electromagnetic wave spectrum. We said that there are 3 different boundaries of interest for us: 0.1 micrometer to 100 micrometer. We call it a thermal radiation boundary. It's radiation. We said that it is. Sorry, one A is missing. Thermal radiation boundary. We said that it's a bit of like a UV, visible and infrared, visible between 0.4 micrometer to 0.7 micrometer visible light. And we also mentioned about another boundary of interest between 0.5 micrometer and 3 micrometer, which we call it solar radiation. We also talked about Planck's law. We said how we are going to calculate the spectral blackbody emissive power, E B lambda, spectral blackbody emissive power, which is a function of lambda and T, wavelength and temperature because of the nature of radiation, C1 divided by lambda 5 e to power of C2 lambda T minus 1. We also said that C1 and C2 are two kind of like a constant that you can find it from your textbook. We also integrated for all the wavelengths. So when we integrated for all the wavelength 0 to infinity e b lambda lambda t d lambda, we realize that okay, it's equal to sigma t4, which is sigma is like a Stefan Boltzmann constant. We also realized that for any temperature constant curve, spectral blackbody emissive power goes through a maximum, which we are not that maximum depends based on the temperature, but where that or at what wavelength it happens is a constant, which is 2897.8 micrometer Kelvin. We call this one Wien's displacement law. We said that okay, this lambda max is not the maximum wavelength, is the wavelength at which the emissive power is maximum for a given temperature. After that, when we talked about the Stefan Boltzmann law, which was I just mentioned, T4, we said that it's for all wavelength. If we want to have it for do the integral for smaller boundaries, like let's say between 0 and lambda, we define another function called blackbody radiation function as rate between 0 to lambda e b lambda lambda t d lambda divided by sigma t4, call it f lambda t, blackbody radiation function. We also said that is between that is if we want to find the emissive power between 0 and lambda. What about if we want to find the emissive power between two specific wavelengths? If we want to find the two specific wavelengths between lambda 1 and lambda 2, so basically it's f lambda 1 lambda 2 t. We said that okay, that can be calculated 0 to lambda 2 b lambda lambda t d lambda sigma t4 minus 0 to lambda 1 v lambda lambda t d lambda divided by sigma t4, which is equal to blackbody radiation function for lambda 2 minus blackbody radiation function for lambda 1. Okay, we talked about all those stories, and after that we defined the blackbody based on its characteristics. We said that the blackbody has three characters that we define blackbody based on that. First, blackbody is the best possible emitter. Second, we said that okay, blackbody absorbs all the incident radiation. So basically, best possible absorber. We proved it based on the concept of thermal equilibrium that for blackbody, in order to be the best possible emitter, it needs to be the best possible absorber as well, and vice versa. And we also proved that the blackbody is a diffuse emitter. Okay, so those concepts we talked about it. If you have any problem, please go to the first lecture and see if you understand everything. If you don't, please go through your textbook, read it, watch the video one more time, and if the problem doesn't solve, you can just like drop me an email and I try to explain it to you. Okay, let me start with the second lecture. To understand the blackbody behavior, there are some mathematical definitions that we need to go through first, okay? Especially because radiation heat transfer, due to its nature, involves extensive use of spherical coordinate. Let me start with plane and solid angle. Plane angle, so it's from very simple math from high school. You see that the alpha is equal to the L divided by R. What was the unit? Radians. You are familiar with this concept, but you might not be familiar with the concept of solid angle, as mentioned here. The differential solid angle d omega is defined by a ratio, which is first the region between the wraps of a sphere, and is measured as the ratio of the surface area of the sphere between the rays to the sphere radius squares, and the unit is steradian. Okay, just have it for now, and after that we are going to work a lot with this differential definition of solid angle. Okay, ds divided by r2. Look at this picture and consider emission in a particular direction from an element of the surface area of dA. The direction will be specified in terms of two angles that we call it zenith angle, we show it with theta, and azimuthal angle, we show it with phi. So for a spherical coordinate we need two angles in order to be able to specify a direction. Okay, so now we have it. So let's try to calculate the solid angle. So we want to calculate the solid angle. Okay, from previous slide we know that the differential solid angle can be defined as ds divided by r2, but here ds, you see that it's a rectangular and can be calculated easily. So ds is equal to r sine theta d phi multiplied by r d theta. So dr is equal to r2 sine theta d theta d phi. Consequently, we know that d omega, which is like a differential solid angle, will be equal to sine theta d theta d phi. What is it? It's a differential solid angle. So of course, if we want to calculate solid angle, we need to do a double integration for theta and phi. To calculate the solid angle associated with the entire hemisphere, we can integrate the differential solid angle for theta between 0 and half a pi and phi between 0 to 2 pi. So we just said that differential solid angle is equal to sine theta d theta d phi, and we said that okay, if we do the integration between theta and pi 2 and phi between 2 pi, we can calculate the solid angle. Let's calculate it. Is 0 to 2 pi, 0 to pi 2, sine theta d theta d phi. So d phi comes out 2 pi, 0 to pi 2, sine theta d theta, and we know that this is equal to 1, then 2 pi stradian. So the solid angle associated with the entire hemisphere we calculated as 2 pi stradian. Okay. The other story that we need to think about is that the differential area of ds here, when we use that, is normal to the direction of viewing, since it is viewed from the center of a sphere. You see that it's normal. I don't know if you can see it properly here, but it is normal to that area. Okay, but let's say what if it's not normal? So in this picture you see that okay, if it's not normal, of course instead of A we are going to use the effective area of dA for emission in the direction of theta, which is the projection of dA on the plane normal to theta. So instead of that we use a cosine theta. So of course if the theta is normal, the cosine of 0 will be 1 and everything will be okay. We discussed that radiation is emitted in all directions into the hemispherical space, and also we spoke about the fact that the radiation streaming through the surface area of ds is proportional to the solid angle of d omega subtended by ds. Okay. Now we have almost all the requirements to calculate the radiation intensity. Okay, so let's first define it. So what we are going to define, we want to define the radiation intensity. We want to calculate it. So it can be defined as the rate at which radiant energy is emitted in the theta and phi direction per unit area of the emitting surface normal to this direction and per unit solid angle about this direction. Okay, if we want to translate this paragraph into like one mathematical correlation, we can say that the intensity of radiation phi, so emission is equal to Q dot E divided by sine theta, unit area of the emitting surface normal to the direction, per unit solid angle about that direction. Okay, so that's the radiation intensity. Now we need to calculate it, but first, before how we are going to calculate it, I want to speak about three radiation fluxes of interest for us in this chapter or in this section. So we are interested in emissive power, we are interested in irradiation, and we are interested in radiosity. What are they? We are going to speak about it, but we want to calculate everything based on these three fluxes. We don't want to deal with lots of fluxes. We just want to know that, okay, what is the emissive power? We want to know the irradiation. We want to know radiosity and be able to calculate it. But here, as you can see, we calculated stuff based on IE, which is radiation intensity, and dq dot E. Basically, we are not that interested in q dot E. We want to see if there is any way to be able to somehow translate it into one of the fluxes of interest, emissive power, irradiation, or radiosity. Okay, so let's see how we can get from dq dot E to one of the fluxes of interest. So fluxes of interest for emissive power dE, we can say that is equal to dq dot E divided by dA, and is 2. So q dot of emission divided by dA is the emissive power, basically. So the differential emissive power, we can define it as a differential q dot emissive divided by dA, and we also said that IE emissive, the direction of phi, is equal to dq dot E divided by dA cosine theta d omega. We also said that d omega is sine theta d theta d phi. Okay, so now we have everything, we can easily calculate it. So differential emissive power is equal to IE theta and phi cosine theta sine theta d theta d phi. Okay, we have it. It's not a rocket science. We just like substitute these definitions into the equation. So we substitute this one here and we substitute this one here. Okay, so of course again it's the differential form of emissive power. We need to integrate for theta and phi to be able to calculate it, and for hemisphere it will be for theta between 0 and half a pi, and phi between 0 and 2 pi. So let's do the calculation. So emissive power basically will be 0 to 2 pi, 0 to pi 2, i.e. theta and phi, sine theta, cosine theta, d theta, d phi. So phi comes out 2 pi, 0 pi 2, i.e. theta and phi, sine theta, cosine theta, d theta. In general, the intensity of radiation emitted by a surface varies with direction, but many surfaces in practice can be approximated as being diffuse. Okay, so good engineering assumption so the surface is diffuse. So when the surface is diffuse, what does it mean? It means that it's independent of direction, so it can come out for diffuse surface, which is a good engineering assumption for many surfaces that we face. We can say 2 pi e, no direction, 0 to pi 2, sine theta, cosine theta, d theta. So the only thing that we need to calculate is this integral. I just like call it a. So basically emissive power is 2 pi i.e. intensity of radiation or emitted radiation multiplied by a, which is this integral. Don't mix this a with surface area. It's not a surface area, it's just this integral. Okay, so let's calculate that integral and see what we get. So a is 0 to half a pi sine theta, cosine theta, d theta. Very simple assumption. We assume that sine theta is equal to u, so cosine theta d theta is du. So basically a is equal to u du, which will be plus c. So a will be half sine theta plus c minus sine 0 to the power of 2 minus c. 1, this is 0, so will be half. Then we have e is equal to pi rot 2. Okay. Until now, we were focused on radiation emitted by a surface. We know that all the surfaces that emit radiation, they also receive radiation emitted or reflected by other surfaces. So the same can be extended to incident radiation. Okay? So now let's define the intensity of incident radiation. So we define the intensity of radiation or intensity of emission, but intensity of incident radiation we show it with II intensity, theta and phi. First let's define it, and after that find out how we can use or find any kind of mathematical correlation to describe it. The intensity of incident radiation can be defined as the rate at which radiation energy incident from the theta and phi direction per unit area of receiving surface normal to this direction and per unit of solid angle about this direction. So if we want to translate this paragraph into one mathematical correlation, we can say that intensity of incident radiation is equal to dq dot I, which is incident, dA cosine theta per unit area of solid angle, d omega. Okay? If you remember, I talked about three fluxes of interest: emissive power, irradiation, and radiosity. Let me show you here. So irradiation is the one that we need to speak here because it's about the incident radiation. Okay, so irradiation, we show it with G. So can be defined as the radiation flux is incident on a surface from all directions per unit area of incident surface. So basically we can define it as dq dot I divided by dA watt per meter. So if we put it into the main direction as well as implement the differential solid angle, which is sine theta d theta d phi, we will have differential irradiation is equal to I, which is the incident radiation phi sine theta d theta d phi. And if we follow the same procedure for irradiation, we can say that irradiation is equal to p pi I m2. Okay, so calculated this one, the flux of interest pi I e. We calculated irradiation of interest pi I incident. Now the only flux of interest which is left is radiosity. Okay, radiosity is basically accounts for all the radiant energy leaving a surface. So you see that, so here we can easily say that radiosity is bigger than emissive power. Why? Because it's emissive plus reflected irradiation. Okay, since it accounts for all the radiation leaving a surface in all direction, it is related to intensity associated with emission and reflection, and can be expressed as emission plus reflection. Okay, so the calculation of the integral will be the same as what we have done with emissive power. Okay, that is basically it for from the basics of radiation here. But let me solve two examples for you to see how we can use these concepts into the practical applications. Okay, so this question is 12.44 of your textbook. As you can see, is like it's one of the simplest question that you can get from this section. We have two small surfaces. They are far from each other. The R is 75 centimeter, and we have the different angle. What is asking us is to determine the intensity of radiation emitted by A1 as well as the temperature of A1. So basically it's focused on the surface A1. A small surface area of A1 emits radiation as a black body. Okay, so the A1 is a black body, and a part of radiation emitted by A1 strikes another small surface A2, oriented as shown in the figure. If the rate at which radiation emits by A1 that strikes A2 is measured to be 278 multiplied by 10 to the power of minus 6 watt, determine intensity of radiation emitted by A1 and the temperature of A1. Let's do a very quick assessment of the question and see what we have and what we need to find. What we have and what we need to find, or what the question is asking us. Okay, what we have is we have the A1, the surface area 3. We know that the A1 is black body. We also have the Q dot 1 to 2 is equal to 274 10 minus 6. So emits by surface 1 strikes to surface 2, and we also have A2, so 8 2. What we need to find? We need to find I1, which is the intensity of radiation emitted by A1 and the temperature of A1 and T1. Okay, TE1. Now let's see how we are going to calculate. If you remember, we say that I1 is equal to Q dot 1 to 2 A1 cosine theta 1 solid angle of 2 to 1. Okay, so it's like a correlation that you can find in your textbook. Solid angle of 2 to 1 is equal to A2 cosine T2 R2. Okay, so let's calculate this one. The solid angle 2 to 1 is equal to 8 to cosine 40 divided by 75 centimeter power of 2. This will be 10.89 10 to the power of minus 4 radian. Okay, and I1 will be equal to 274 10 minus 6 watt divided by A1 3 10 to the power minus 4 M2 divided by cosine 55 multiplied by 10.89 10 to the power of minus 4 radian. The answer will be 1460 watt square meter radian. Okay, so we found the intensity of radiation. Now how we are going to find T1, because the question is asking for T1 as well. If you remember, it said that A1 is a black body. It's a black body. Okay? The intensity of radiation, or intensity of radiation emitted, we remember that it was E is equal to pi that I E. Okay? So E1 B, because it's a black body, is equal to P that I E1, which just calculated for surface 1. Okay? You remember that it is T1 to the power of 4 pi E1. Why? This is sigma Stefan Boltzmann law. Why? Because A1 is a black body. Black body. Then T1 will be pi 1 divided by sigma to the power of 4. If we have all the information, we just need to put it. So the pi is the radian, multiply by 1460 watt is the radian divided by 5.67 10 to the power of minus 8 watt square meter K4 14. The answer will be 533 Kelvin. Okay, as simple as that. So basically it's the simplest question that we can get for this chapter, but let's solve another question, and let's see how we can work with the other one. Okay, so this example is saying that what we got here is a surface emits as a black body. Okay, so we know the black body, we have the temperature. What is the rate per unit area at which it emits radiation? So what is asking? Rate per unit area emits radiation is asking for emissive power. Okay, one of the fluxes of our interest, watt square meter, over all direction corresponding to theta between 0 to 60 degrees and over the wavelength interval between 2 and 4 micrometer. Okay, so let's again quickly assess what we have and what we need to find. This will help us to have a better understanding when we are going to solve. Okay, what we have, we know that the surface is a black body. Okay, we know it. T is 1500. We know this one. Theta between 0 and 60 degrees, and the interval for wavelength is between 2 and 4 micrometer. What we need to find is emissive power. But you might say that, okay, emissive power is so easy, it's sigma T4. No, because it doesn't want us to find the emissive power for all the direction and all the wavelength. We are restricted to a specific direction and a specific wavelength, not for all the emissive power. Okay, so it's not EB. This one, yeah, we could quickly say that is sigma T4. This one is asking for emissive power of black body 4 in the direction and theta, not. So we need to take this theta and wavelength into consideration. Okay, basically what we need to do is doing the integration. So emissive power basically is equal to, for the wavelength of 2 to 4, for theta between 0 to pi 3, for phi between 0 and 2 pi, we have black body, cosine theta, sine theta, d theta, d phi, d lambda. Okay, as we mentioned, the surface is black body, so it's a diffuse emitter. It can come out of the integrals for direction, so it will be 2 to 4 b lambda, and we have like a 1 double integral for direction, cosine theta, sine theta, d theta, d phi, d lambda here. Let's say this is A, so basically E will be to 4 meter I b lambda A d lambda. What we need to do is just finding A here. Okay, let's try and see if we can find A. So A basically was equal to 0 to pi 3, 0 to 2 pi, cosine theta, sine theta, d theta, d phi. Use the same substitute. We assume that sine theta is equal to u, so cosine theta d theta is du. So basically it will be between 0 to pi 3 u du, which is 0 to pi 3. So basically it will be 0.75 divided by 2, and finally A will be 0 to pi 0.752 d phi, which will be 2 pi 0.75 divided by 2 will be 0.75 pi. So this is A. So first we calculated this, the cosine theta, sine theta, d theta between 0 and pi 3, and after that we put it here. Okay, so finally emissive power will be between 2 to 4 meter I b lambda, 0.75 pi d lambda. So 0.75 pi comes out of the lambda, sorry, pi can stay inside. It will be 2 micrometer to 4 micrometer I b lambda d lambda. Is it familiar with you? Yes, it is. Let's calculate and see it. If you remember, we said previously that EB lambda T is equal to pi I B lambda and T. So basically we can say that E is equal to 0. Sorry, let me put 0.75 2 micrometer to 4 micrometer P I lambda D lambda. Okay, so multiply it by EB lambda and T, so it will be 0.75 EB for black body the whole, 2 there to 4 micrometer pi IB lambda divided by EB D lambda. What is this? Because this one, it's EB lambda and T, this is EB, so we know that this is black body radiation function. Remember it? F lambda T is equal to 0 to lambda EB lambda T D lambda divided by EB, which was equal to sigma T4. So it will be 0.75 EB. It's between two intervals, so it will be function of 0 to 4 micrometer minus function 0.2 micrometer. Okay, now we go to table 12.2 of the textbook and we can find the answer. So let me first write here the E. So E was, E is equal to 0.75 EB 0 to 4 minus F 0.2 micrometer. Okay, 0.2, 0.4. So lambda 1T is equal to 2 micrometer multiplied by 1500, so it will be 3000, this is Kelvin, 3000 micrometer Kelvin. We go and we find 3000, so we find that one. The F of 0 to 2 micrometer, from the table we have it 0.273232. The same story will happen for the second one. Lambda 2T is lambda 2, which is 4 micrometer multiplied by 1500 Kelvin. It's 6000 micrometer Kelvin. We go to the table, 6000, so F 0 to 4 micrometer is equal to 0.737818. So now the only thing that we need to do is to put everything into the equation. So equation was E is equal to 0.75 EB, that F 0.24 micrometer minus F 0.2 micrometer. We calculated from the table F 0.2 micrometer is 0.273232. F between 0 to 4 micrometer is 0.737818, and EB we know that is equal to sigma T4. It's equal to 5.67 10 to the power minus 8 watt square meter K4 multiplied by 1500 Kelvin to the power of 4, which will be the final answer. So we have these three, so the final answer E is equal to 10.0017 10 to the power of 4 5 watt square meter. Was a bit more complicated, but if you follow the same procedure, it's very simple to follow. Okay, maybe needs a bit of like a math to be able to calculate it, but nothing extraordinary or rocket science. Okay, let's finish this lecture with another example. This is the last question that we are going to solve in this lecture. Let's follow the same procedure and see what we have and what the question is asking us. So what we have, what we need to find. Okay, so it's saying that we consider a large isothermal enclosure that is maintained at the uniform temperature of 2000 Kelvin. Calculate the emissive power of the radiation that emerged from a small hole on the enclosure surface. What is the wavelength lambda 1 below which 10% of the emission is concentrated? What is the wavelength lambda 2 above which 10% of the emission is concentrated? Determine the maximum spectral emissive power and the wavelength at which this emission occurs. What is the irradiation incident on a small object placed inside the enclosure? Okay, well, what we have is, we know that the enclosure is at the temperature. We have the temperature of enclosure at 2000 Kelvin. We also know that it's because the large isothermal enclosure is the same concept that we use to prove the black body characteristics. So the emission from the whole of any isothermal enclosure have the characteristic of black body radiation, because basically what he's saying that is everything is the same as the same concept we used for characterizing of black body. Okay, so the emission from the hole of any isothermal large enclosure have the characteristics of black body. Didn't say it directly, but from the question we can get it. Okay, what we need to find. First, what is the wavelength lambda 1 below which 10% of the emission is concentrated? Emission. So it's what is asking is emissive power, but not the whole emissive power, like wavelength below the 10%, below the wavelength below which and above the 10% of the radiation is concentrated. The other that is asking is the maximum spectral emissive power and the wavelength at which this emission occurs, so Wien's displacement law, and is also asking for irradiation Okay, so we have a lot to calculate here. Okay, so it's saying that emissive power, emissive for top and below 10%. What is EB lambda T, lambda max, and irradiation? So we need to calculate all of them. So let's start. First, emissive power. Okay. So emissive power E is equal to ET sigma T4Y, because we said that is a characteristic of a black body. 5.67 10 to the power of minus 8 watt M2K4 2000. Sorry, let me see what temperature was that. Yeah, 2000. So 1000 to the power of 4. You see, it was easy, looked difficult, but it was not. Why? Because of paying attention to what we have and all the definition of black body. The second is saying that what is the wavelength lambda 1 below which 10% of the emission is concentrated? What is the wavelength lambda 2 above which 10% of the emission is concentrated? So basically what it is asking is F0 to lambda 1 is 0.1 and F to 0. Lambda 2 is equal to 0.9. 10 below, 10 high. So what is asking is finding this lambda 1 and lambda 2. Okay? So how we are going to find it? We need to go back to the table. Here, the table. And we need to interpolate. So let's say 1, we said that here between these two we need to interpolate for 0 to lambda 1 for 0.1 and 0.9 between these two. F0 to lambda 2 is equal to 0.9. Okay? So I've done the interpolation for F 0. Lambda 1 is equal to 0.1. Lambda 1 T will be 2.2195 micrometer Kelvin. We know the temperature, so the lambda 1 will be 2195 Kelvin divided by temperature, which was 2000 Kelvin. We have 1.0975 micrometer. For F0 to lambda 2 is equal to 0.9. After interpolation, lambda 2T will be 9382 micrometer Kelvin. So lambda 2 easily can be calculated, divided by 2000 Kelvin is equal to 4.691 micrometer. Okay. What else we need to calculate? Spectral emissive power and wavelength associated with the maximum emission. How we can calculate the spectral emissive power? Planck's law. So EB lambda T, Planck's law, if you remember, was C1 lambda 5 E C2 lambda T minus 1 C1 2 PHCO2 from page 718 of your textbook. Phi is equal to 3.74177 10 to the power of 8 micrometer to the power 4 divided by 2, and C2 is HCK 1.43878 10 to the power of 4 Kelvin. To calculate that, we need to have lambda max, but based on now we have the C1, now we have C2. Here we need to put the lambda max. Why? Because it's asking to find the spectral emissive power associated with lambda max. Okay, we have the temperature here, no problem. We have C1, we have C2. The only thing that we need is finding lambda max and put it into this equation. Lambda max, how we can find it? From Wien's displacement law and law. So lambda max T is equal to 2897.8 meter Kelvin. So lambda max will be equal to 2897.8 micrometer Kelvin divided by 2000 Kelvin. So it's equal to 1.4498 micrometer. We put this one into the equation. So we have lambda max, we have C1, we have C2. We can calculate the spectral black body emissive power. So EB lambda T for lambda max of 1.4489 micrometer and temperature of 2000 Kelvin is equal to C1. We have that is equal was 3.74177 by 10.8 watt micrometer to the power of 4 M2. So lambda max to the power of 5 e to the power of C2 divided lambda T minus 1. I don't want to make it here very complicated, but if we calculate this one, we will have the final answer EB lambda will be equal 4.11769 10 to the power of 5 watt square meter micrometer. It's not done, still another one is left, because if you let me go back to the equation. Is asking what is the irradiation incident on a small object placed inside the enclosure. Okay, so it's asking us to calculate the irradiation as well. Irradiation on the small object inside the enclosure. So we just talked about that the small enclosure, we said that all the stories, it will be treated as a black body. So irradiation will be equal to emissive T4. Why irradiation is the equal of the emission? Because of the characteristic of black body. We said that black body is a perfect emitter, and we said that the black body is a perfect absorber. which absorbs all the incident radiation. So the amount of emission exactly the amount of energy that comes in, it's exactly the same as amount of radiation heat transfer goes out. So it will be equal to 9.07 10 to the power of 5 watt square meter. We just calculated the first place. Okay, that's the first part of or bunch of examples that we solved. This example and the previous example, the last two ones are important ones, and more or less they are the kind of question that you will face during the exam. Okay, so go through them and try to do it at your work step by step, exactly the same way that I did. Maybe you say that you did it fast, but try to work at your home by yourself and try if you can get the same answer. If you have any question, come back, watch the video one more time. If you can't get it right, just drop me an email and I try to explain it to you. Thank you for your attention, and that was the end of our second lecture.